The word field carries a strange reputation in physics. It often sounds abstract, almost secondary, as if it were a mathematical convenience rather than something real. Objects feel tangible. Motion feels immediate. Fields can seem like an extra layer added only after things become complicated. That impression turns out to be backwards. Fields are not an advanced decoration placed on top of physics. They are one of the main ways physics explains how the universe actually works. The puzzle appears immediately. If fields matter so much, why do they not announce themselves in everyday experience? Why does a table feel solid while a field feels invisible? The answer begins with how physics once described interactions. Early explanations focused on direct contact. One object pushed another, pulled another, collided with another. That picture works well when things touch, so it felt complete. Then nature introduced situations that refuse to fit. A magnet attracts iron without touching it. An electric charge influences another charge across empty space. Gravity acts between Earth and Moon with nothing visible in between. Something influences motion where no object seems to be present for a long time. This influence was described as action across distance. That phrase sounded like an explanation, but it avoided the real issue. It said that something happened without saying what existed in between. Fields entered physics as a way to take that in-between seriously. A field assigns a physical condition to every location in space and time, with that condition determines how an object placed there will move or respond. Instead of asking how one object reaches another, physics asks what the surrounding space is like at each point. This is the core idea. Space itself carries information about influence. When a charge exists, the space around it has an electrical condition. When mass exists, the space around it has a gravitational condition. Other objects respond when they occupy those regions. This removes the need for distant objects to communicate directly. Each object interacts only with what exists locally, right where it is. And once this idea is accepted, many things suddenly fit together. Electric forces, magnetic effects, gravitational attractions, and light all find their place within the same framework. Each corresponds to a field with its own behavior, its own rules for how it changes and how it influences motion. The fields also solve a deeper issue. They allow interactions to propagate through space rather than appear instantly everywhere. Changes, travel, causes, remain connected to nearby effects. Physics regains locality. At this point, the idea of empty space becomes less simple than it once seemed. Even regions with no particles still possess physical properties. Fields can exist there. They can store energy. They can influence motion. This leads naturally to a question that refuses to stay small. If fields fill space and guide how objects behave, where does reality truly reside? In the particles we see or in the conditions of the space they move through? That question is not decorative. It determines how modern physics understands forces, motion, and even what it means for something to exist at all. That question pulls attention forward because the idea of fields only becomes solid once it is anchored to something concrete. So let's ground it. Take gravity not as a formula, not as a law written on paper, but as something that actually happens. You release a ball and it falls. That event feels simple. The usual story says Earth pulls the ball. End of explanation. But notice what that story hides. The ball does not touch Earth. There is empty space between them. If influence passes from Earth to the ball, it must pass through that space. Physics does not allow influence to leap over space without accounting for what happens in between. This is where the field enters, not as a metaphor, but as the thing doing the work. At the most fundamental level, a field is a physical quantity assigned to every location in space and time. Each location has a value, even if no object is present there. That value determines how an object would respond if it were placed there. That sentence is dense. So let's unpack it carefully. A field exists everywhere, not only where particles happen to be. It does not wait for an object to arrive in order to exist. It already assigns conditions to space itself. Objects respond locally to those conditions. In gravity, the mass of Earth establishes a gravitational field throughout the surrounding space. The ball does not feel Earth directly. It responds to the gravitational condition of the space it occupies at that moment. As the ball moves, it encounters different field values, and its motion changes accordingly. Nothing reaches across space, nothing acts at a distance. Everything happens locally. This is the core mechanism. Once this idea is absorbed, many familiar effects stop feeling mysterious. Electric charges influence other charges because the space around them carries an electric field. Magnets influence iron because the space around them carries a magnetic field. Light exists because changes in electric and magnetic fields travel through space. Fields are not carriers of messages between objects. They are the environment in which objects exist. Here is where common sense begins to resist. Everyday thinking treats space as empty, passive, nothing more than a stage where events occur. Fields overturn that picture. Space itself acquires physical properties. It can be stretched, distorted, energized, and altered. This does not mean space turns into a substance. It means space has measurable conditions that affect motion. A helpful analogy, limited but useful, is temperature in a room. Temperature assigns a number to every location. A cup of water placed in one part of the room warms or cools based on the local temperature. The water does not communicate with the heater across the room. It responds to the condition of the air right where it sits. A field works similarly, except the number it assigns determines force, motion, or energy rather than heat exchange. This analogy exposes where intuition fails. Common sense expects influence to come directly from objects. Physics shows that influence comes from fields already present in space. Objects modify fields. Fields guide motion. Once this is understood, the role of particles changes. Particles no longer serve as tiny sources that reach out to one another. They become localized excitations interacting with fields. This is not interpretation layered on top of equations. It is how modern experiments are described. In fact, physics has gone even further. In contemporary theories, fields are treated as more fundamental than particles. Particles appear as localized disturbances of underlying fields, not as independent building blocks. That idea sounds radical only because everyday experience hides fields so effectively. Now consider a classic experiment that makes fields unavoidable: electromagnetic waves. When an electric charge accelerates, something propagates through space and can be detected far away. No particles travel from the charge to the detector. What travels is a change in the electromagnetic field. That change carries energy and momentum. It can move objects. It can heat matter. It can trigger chemical reactions in your eyes. Light itself turns out to be a field phenomenon. This result leaves no room for fields to be bookkeeping tools. They carry energy. They evolve over time. They influence motion. Those are physical traits. Another place intuition breaks is the idea of emptiness. In field theory, space without particles is not featureless. Fields still exist there. They can fluctuate. They can store energy. They can interact. This explains why removing all matter from a region does not remove physics from it. Fields remain, effects remain possible at the most basic level. Then a field is a way physics assigns structure to space and time. It tells space how objects will behave, and tells objects how to move without direct contact. Fields answer a question. Objects alone cannot answer how influence travels and how it remains local. That is why fields appear everywhere once they are introduced. They unify forces. They connect motion and interaction. They replace distant action with local response. And this leads to a deeper consequence that follows naturally rather than dramatically. If fields define the physical condition of space, then understanding the universe means understanding how those conditions change, interact, and constrain motion. Objects become participants in a larger structure rather than isolated actors. That idea does not reduce the importance of particles. It places them where experiments consistently put them, as localized features within an extended physical environment. With this understanding, talking about fields becomes easier, not harder. One stops asking where the force comes from and starts asking what the field is doing at each location. That question has precise answers, and it leaves behind a puzzle that grows directly from everything said so far. If fields fill space and carry energy and influence, what governs their behavior? And why do different fields follow different rules? That question emerges naturally from understanding what fields are, not from adding anything extra. Once fields are accepted as real physical features of space rather than as mathematical conveniences, their consequences begin to stack up in ways that quietly overturn familiar expectations. One of the most striking results is this: influence no longer belongs to objects alone. It belongs to space itself. A charge does not carry its electric influence like a personal possession. A mass does not carry gravity tucked inside it. Each establishes a condition around it, and that condition exists whether or not another object is nearby to notice it. This changes what it means to explain anything. In physics, instead of saying this object acted on that object, the explanation becomes this configuration of the field led to this behavior. The cause is not a hidden push. The cause is the state of space at each location and how that state evolves. At first, this sounds like a subtle rephrasing. It is. Not. It resolves a paradox that haunted physics for centuries. How something here can affect something far away without violating causality. Fields answer this by refusing to let influence leap across space. Every effect travels through neighboring regions. Nothing skips steps. This immediately ties fields to time. A field does not merely exist, it changes. Those changes spread at finite speeds. Light is the most familiar example, but it is not unique. When a mass moves, the gravitational field around it adjusts. That adjustment propagates. Distant objects respond later, not instantly, but cause and effect remain ordered because fields evolve locally. Here, intuition often stumbles. Everyday reasoning expects the source to do something to the target. Fields insist that the source alters space and the target responds to the space it occupies. The action is indirect but complete. Another surprising result follows. Fields themselves store and transport energy. This point cannot be softened. Experiments force it. Light carries energy across empty regions. Electromagnetic fields can exert pressure. Gravitational waves transport energy between massive systems. These effects cannot be explained unless fields are treated as physical entities with energy and momentum. This reshapes conservation laws. Energy is no longer tracked only by watching objects. It must also be tracked in space itself. Energy can move without matter moving. A region can gain or lose energy purely because the field there changes. Once fields are included, conservation becomes exact again. Without them, it appears violated. This is not a technical detail. It reveals a unified picture. Motion describes how objects respond to local field conditions. Forces describe how field conditions vary across space. Energy describes how those conditions are distributed and transformed. None of these ideas stand alone. Fields tie them together. A deeper unification appears when multiple fields are considered at once. Electricity and magnetism merge into a single electromagnetic field. What once looked like two forces becomes one structure viewed under different circumstances. Light appears as a self-sustaining change in that structure. This result was not guessed. It was forced by consistency. Without fields, the connection makes no sense. With fields, it becomes unavoidable. Gravity extends the idea even further. Mass alters the gravitational field, and objects follow paths shaped by that alteration. Modern descriptions go so far as to link the gravitational field to the geometry of space and time themselves. The details grow complex, but the organizing principle remains unchanged. Local conditions guide motion. At this stage, a deeper question arises naturally, not as philosophy, but as consequence. If fields exist everywhere, even where no particles are present, then what does empty space mean? Physics answers carefully. Space without matter is not featureless. Fields remain. They can fluctuate, they can carry energy, they can influence future events. Removing particles does not remove physics. This result feels counterintuitive because everyday experience treats emptiness as absence. Fields replace that idea with structure. Space becomes an active participant. This perspective also resolves another apparent paradox: how particles can behave as both localized and extended. In modern physics, particles appear as localized excitations of fields. The field provides the extended structure. The particle marks where activity is concentrated. Nothing mystical is added. The description simply moves to the level that experiments demand. With this shift, explanation itself changes character. Instead of asking which object caused an effect, physics asks how a field configuration evolved. Instead of tracking invisible pushes, it tracks measurable conditions across space and time. This approach applies cleanly to atoms, circuits, stars, and galaxies without changing its language. That scalability is not accidental. It signals that fields capture something essential. At this point, the meaning of a field can be stated plainly. A field is a physically real assignment of quantities to space and time that determines how objects behave locally and how influence propagates. It exists independently of whether matter occupies a given location. This definition matters because it explains why physics relies on fields so heavily. Without them, influence has no place to exist. With them, locality, causality, energy, conservation, and motion align into a single framework. Understanding fields reshapes how reality itself is viewed. Objects no longer sit inside space as independent actors. They participate in an environment that they both affect and respond to. Space ceases to function as a passive background, and becomes part of the physical story. Objects are not erased by this view. They are placed in context. The consequence is practical rather than abstract. Once fields are understood this way, explanations become transferable. The same reasoning explains why a compass turns, why light travels, why charges interact, and why gravity guides motions. No special cases are required. No invisible mechanisms are invoked. That marks the transition from knowing how fields behave to understanding what they mean. Fields show that the universe organizes influence locally, spreads change through space, and then forces consistency without shortcuts. They explain why physics can describe interaction across vast distances without contradiction. With that understanding, fields no longer appear as an advanced topic set aside for later study. They appear as one of the basic ways interaction is possible at all. Fields occupy their proper place in physics not as an added layer but as a structural support. They provide a way to describe influence, motion, and energy that remains consistent across distance, scale, and perspective. A coherent picture follows naturally. Objects possess mass, charge, and other properties. Those properties establish fields throughout space. The fields assign physical conditions to each location. Other objects respond to those conditions locally. Motion follows from how those conditions vary across space and evolve through time. Nothing in this picture acts alone. Objects and fields form a coupled system. Objects shape fields. Fields guide objects. Physics relies on both because experiments demand both. What physics knows about fields is substantial and precise. It knows how electric, magnetic, and gravitational fields behave. It knows how they change, how they carry energy, and how they influence motion. It knows that changes in fields propagate at finite speeds. It knows that conservation laws remain valid only when fields are included. These conclusions are enforced by measurement. Physics also knows that fields can exist without matter present. Regions of space with no particles still possess physical properties. Fields there can store energy and influence future events. Removing matter does not remove structure. What physics does not yet know is whether all fields arise from a smaller set of principles or whether they are fundamental in their own right. It does not yet know how gravity fully fits with quantumized descriptions of other fields. It does not know whether space and time themselves emerge from something deeper. Those unknowns define the frontier, not the foundation. What remains secure is the role fields play in explanation. Any deeper theory must still account for local influence, finite propagation, energy stored in space, and consistent behavior across observers. This understanding changes how familiar phenomena are interpreted. A compass turning reflects a magnetic condition at its location. Light reaching the eye is energy carried by a changing electromagnetic field. Gravity guiding planets reflects motion shaped by the surroundings. Gravitational field. The same reasoning applies everywhere. Explaining interaction no longer requires imagining distant objects acting directly on one another. It requires describing the field present at a location and how it changes. Fields also alter how space itself is understood. Space possesses physical conditions that matter. It participates in how motion unfolds. It stores and transfers energy. This gives space a role without turning it into a substance. Seen this way, fields are not abstract additions to physics. They are one of the basic structures that make motion, force, and energy intelligible at